Go ahead. You have the microphone?
Yep. So then let's just start, because I heard we have a tight schedule. So my name is Jan. I'm here to present some quick research I've done for the German Aerospace Center on generic polyphase filter banks on a GPU with CUDA. So yeah, I'm working for a German Aerospace Center in the Satellite Communication Navigation Institute. It's the Satellite Networks Department, and I do mostly software-defined radio. So short outline of the talk. So we start with the mandatory motivation. Then I want to give a short introduction into the CUDA system, a short introduction into polyphase filter banks, what they are and why they are so cool or not so cool. Translation of the polyphase filter bank from, like, you have the DSP, how do you get it to CUDA? And then some results, and then some release plans for a library that is open source that actually does that. So, motivation. Once upon a time there was a space project that I've been working on. It was kind of a multi-frequency random access scheme. So we have several numbers of carriers. In this project it was like this, a 15, 30, a 45 carrier. And on the receiving end, we have to separate them somehow. So I remember Tom's talk in Karlsruhe like years ago. Like, hey, let's do the PFB thing. That sounded cool. So I did some calculations. And if you have 45 carriers, the problem is if you have all of them at once, you have like 45 times the bandwidth. So that could be a lot. And also for the actual channels, the restrictions were quite tight, so we only had 12 to 15% guard band between information signal and then the next channel. So this is quite steep. We needed oversampling. Here it says at least 3 times oversampling is needed. This is where we are right now. At that time we had to do at least 8 times oversampling. So it's quite a lot. So when we did the filter design, or I did the filter design, we came up with up to 1500 tab filters. So if anybody knows something about FIR filters, that's a huge filter. So I did some tests. I wrote a generic CPU version of that. Yeah, that was me when I figured out what I had to do. So I wrote a generic CPU implementation of that. I just used a 1000 taps filter, just used 35 dB rejection, which might be okay, might be not okay. I did the original 9 times oversampling, and I came up with 2 megasamples per second. Well, I needed 4, so it was not fast enough. I tried to look into how I could optimize it or optimize it even more for x86 processors. But actually the filtering was all like maxed out from optimization already. I could have optimized the FFT somehow because I could not use FFTW, which kind of sucked. But that would be like way too much time. So let's try it on CUDA. I had some experience with it, so let's do it. So CUDA, what is it? CUDA is NVIDIA's framework for general purpose programming on graphics processing units. It's mostly used, I think, for scientific computing, where you have a huge problem that you can somehow parallelize a lot, and you don't want your simulations to take years or a month or whatever. Yes, it uses the massive amount of available compute cores inside the GPU. So, for example, the GPU that we're using has like 2000 CUDA cores, which is way more than x86 or so has. Yes. So how is a GPU built? So normally a GPU has, for NVIDIA in this case, has several streaming multiprocessors. These you can think of as like the CPU you have in your normal PC, but you have several of them. In our case it was 7. I'm not sure how far they go up, but you can get one streaming multiprocessor in the low-end graphics card. The high-end one have 7 or 8 or something like that. Each of these streaming multiprocessors has lots of cores, like your normal CPU on your PC. But instead of 4 cores, the CPU that we used had 192 cores, if I'm correct. So also a lot more than your normal x86 CPU. The instruction that they use, or the structure, is a single instruction multiple threads structure. So basically what they do is they take one instruction, they broadcast it over several threads, and all the threads do the same instruction at the same times. Also, you have some different kind of memories on your GPU that are actually really important, that you know what they do and how they do it. You have the global memory, which is what they will sell you on the box. This is like, you get the new GTX 970 with 4 GB RAMs, which are actually just 3.5 GB. This is really slow. It's way faster than DDR3 or something like that, but it's for GPU, it's slow. Then you have the on-chip memory. This is tied to a specific streaming multiprocessor, so all the cores in the multiprocessor share all this memory, which is faster, way faster than the GDDR5 RAM. And then, of course, you have the registers, like any CPU structure, that are blazingly fast and way faster than anything else. So CUDA tries to use that architecture as best as possible. So first thing what it will do, it will build up a grid. And probably I'll just go to the next slide. So this is how CUDA structures the threads that it will run to match the graphics card architecture. So you have here this grid. This is what you have to define in your program. It can be up to 3-dimensional. It can be 2 or 1-dimensional. That's up to you. For visualization, I took the 2-dimensional case, so we have an X dimension and a Y dimension. Each position in this matrix, you could call it, consists of a thread block. A thread block is also just a compilation of threads that will run on one streaming multiprocessor. And inside each of these thread blocks, then you have the individual threads that execute the instruction that you want them to execute. So the way this works is that each of these blocks has a unique ID inside this grid. So you can access block 22 or access block whatever, a 2-dimensional ID that you give them. And each thread inside the thread block also has a unique ID within the thread block. So if you know the ID of your thread block and the local ID of your thread inside the thread block, you can basically access a thread inside your program. What this thread scheduler now does and how he executes those threads is he will collect the thread blocks, assign them to one streaming multiprocessor, and then it will further group these threads inside into bundles of 32 threads, and they are called a warp. And these 32 threads are actually the threads that are going to be executed simultaneously, and you have to be a bit careful. We will come to that later, how you do calculations or anything inside those warps, because the interaction between them is kind of special. So yeah, that's that. You have some performance bottlenecks that you can run into very easily while doing your GPU, and then you put your program into the GPU and you think, well, it's not really fast. So these are some of the problems that you have. First one is global memory. It's not really fast, so you want to minimize the usage in any case. But even if you have to use it, and you have to use it at one point, you have to make sure that all your reads and all your writes to the memory are coalesced. What does that mean is that consecutive threads access consecutive memory, because then what the architecture can do is it can load just one cache line for all the threads that need data, and then distribute the cache line to all the data inside the cache line to all the threads. This will be one load for several threads. If you cross the cache line, then of course it has to load 2 cache lines, which might be way more loads that you would actually need for your instruction or whatever, and then you just waste bandwidth. So be careful about that. Then, if you're using the shared memory, you have a similar problem. So shared memory can also be accessed in parallel if you access several banks in parallel. And how the graphics card will structure this memory is that consecutive 32-bit words are in a different bank. So if your threads or consecutive threads just access a 32-bit word, that is where the memory is consecutive, they can also load all the data in one go. If two threads access the same memory bank, then of course you have two loads and you're wasting memory bandwidth. Then branching is also a difficult topic because it's a single instruction multiple thread architecture. So you want your threads to, or the threads have to do one instruction that is the same on every thread inside a warp. So if you have a branch, it might be that one thread inside a warp has another instruction than the others. So these threads then would have to be executed in serial, because which instruction would you execute then? So yes, these are the three main performance killers that can come up when you do GPU programming. And if you're wondering why does my code not run as fast as I think it should, go to this list. So now, polyphase filter banks. What are they? So basically, polyphase filter banks are used, for example, if you want to reduce computational complexity within resampling filters in general. Whether you decimate or interpolate, it really doesn't matter, but they're used for that. Then what you can also do, if you have a scheme like we had in our project where you have separate channels, you can separate one channel with a polyphase filter bank, but you can also separate all channel at once in one go, which is the cool thing about these polyphase filter bank channelizers. What you can also do is you can take several separated information signals and then distribute all of them into a wider spectrum. This is what the synthesizer does, which we also have implemented, but in this talk I'm going to concentrate on the channelizer because there is already enough stuff to do. So what you would normally do if you would extract a channel that has 1/n of the total bandwidth of your of the signal that you recorded is, well, you could first mix your signal to baseband and then do a low pass FIR filter over it, because you have to do this to get rid of all the aliasing when you downsample. You can also switch this. You can first do like a bandpass filtering and then do the down conversion. Of course, and then you can downsample the signal. The problem, as I said, with this is if you have a small channel compared to the overall bandwidth, your filters will get very steep and they will get very computational heavy. Polyphase filter bank somehow help in that respect. So the polyphase filter bank, what it does is it basically takes your filter tabs or your filter impulse response and then splits them into the n different phase shares or the phase parts that the filter has, which I will show you in a second. So this is like a tab representation of your filter, right? You have 16 tabs from tab 0 to tab 15. And normally you would just like shift your signal through that in one go, like serially, and then you get the output. So now we have the PFB will split these into the tabs. So you have like the first phase part are the red tabs, and then the blue ones are the second phase parts, and so on. What you can do then is you can reorder those tabs and then basically build new filters that are now four tab filters. So in total you still have 16 tabs, but you have they only have 4 tabs and you have 4 filters. This will help in a regard that if you know how computational complexity grows within a filter, it's if you want to sample a signal, it's n square. So now we have basically n divided by 4 squared times 4, which is way better than the usual filter complexity. We actually have divided the computational complexity by 4. So what we will do now is we will get samples from from your source. The first sample will go to the first filter, the second sample will go to the second filter, and so on. We just switch through all the filters. When we are down, we go up again. Basically, what you can think of it in a simple way, or how I always visualize it, is if you downsample the signal, what you actually do is you compute all your 16 output samples, and then you throw away 12 of them. And if you would map that to your filter operation, it's like you kind of just do a snapshot of your filter every 4 computations, and this is actually what it does. In the end, everything gets added together, and then you have your resampling filter already. So if you want to now extract a channel, you basically have to know where your channel is, and then down convert the channel by applying a multiplication with a complex wave. If you do an FFT after your filtering, you get all the channel at once, and yeah, basically you do just one filtering, do one FFT, and get all channels that you want. So yeah, you can also do some different things. You can oversample the output of the channel, which is basically you manipulate this commutator. So instead of, for example, if you want to oversample it by a factor of 2, you don't shift every input. Basically, the first sample goes to T0 and then gets shifted to T4. No, then it gets shifted to T2 actually. Yeah, if you want to synthesize instead of channelize, you can basically do the same operations, but you just reverse it. You first do the FFT, then do the filtering, etc. So how you could translate it into CUDA. So if you're familiar with how CUDA works and you want to do all this basically consecutive memory access, all you do is going to shuffle. So the channelizer, as we saw, consists of 4 operations. We have to shuffle the input stream from a serial stream to this parallel stream. We have to do the polyphase filtering. We have to do the FFT. And after the FFT, we have to parallel to serialize the signal again. So input shuffling. Actually, I don't like this slide, and I don't like how I implemented it in my library. So I took the easy road and said, okay, if you basically shuffle stuff, you either read a core list or you write core list. There's nothing you can do. One of the memory loads will be uncoalesced. So I decided that I coalesce my read because this is somehow the more logical, or was more logical to me, and then write like scattered. The problem with this is if you want to read then coalesced, you basically take your thread blocks and then you have an X dimension in your thread blocks that is the number of your channels. And if you remember that the scheduler tries to bundle the 32 threads to a warp and then execute them, and it starts on the actually in the first dimension of the thread block. If you have less than 32 channels, you're not going to end up with a whole warp. So in my case, where I had 45 channels, it probably didn't make that much of a difference. But if you have less than that, 32 channels, it might make a difference. So I'm going to revisit that and see if it stays like that. So filter operation, yes, we have a basically 2-dimensional grid and 2-dimensional thread blocks. The first dimension in the block computes basically several input samples because we want to maximize out our GPU, and just calculating one sample output, we would still have a lot of threads idle. So yeah, these are compute several input samples at once, or process several input samples at once. The second dimension, the Y dimension, takes care of if I want to oversample the output. This is taken care of in that one. The first dimension of the grid basically represents how many channels I want to have, and the second dimension of the grid is just there if we don't have enough don't have enough threads already executing, then those will provide additional concurrency. Just one thing, I want to show you how that the code for that looks like. So the actual filtering is Wait. Yes. The actual filtering is just these lines. The rest is just shuffling. Sorry. This is shuffling. What the? So no marking. So this is shuffling of the memory, and all the rest is just finding out in which thread I'm actually. So yeah. This is basically all what you do inside your code in CUDA. You try to find out where the hell you are. So, yeah, if you a couple of other things for the filter operations, we go to shared memory. We try to avoid bank conflicts, which is not that easy because we have actually complex samples, which are 64-bit, so not the 32-bit words that we would need for the loads from shared memory. As far as the compiler output concerns, we don't have any registered or shared memory spills. That's always good. The FFT is just a QFFT, which is provided by CUDA. I mean, it's fast, it's convenient, so why not use it? The output shuffling is, because I was actually lazy, implemented on the host CPU for now. This might change as well. I don't expect much of a performance boost, maybe in a 1-digit percentage per area, but it would be nice to have everything on the GPU. For me at the time, it was plenty fast enough. So we have some results. So this is 32 channel separations with no oversampling. The prototype filter was a 437 tab filter, so rather small. And here we see we have benchmarked the GTX 970 against the trusty old GNU Radio Polyphase filter bank. And actually, the Polyphase filter bank of GNU Radio is doing very good. This is for GPP really remarkable. What we see, we got to 160 megasamples with the CUDA implementation, which is roughly 4 times as fast as the CPU version. This is the actual filter that we use in the projects for the 45 channel case. So we have 3 times oversampling, 45 channels, 1501 tabs. So we see this time we actually have 3 GPUs. There is also the GT720M, which is a laptop, a really low-level laptop, a GPU with just 1 streaming multiprocessor. And you see we still get above 100 megasamples with the CUDA implementation on the GTX 970. 720 GT is a bit worse, or far worse, with 14 megasamples, which would still be okay in our use case. And then the CPU version is actually not that much slower than the GTM 720. So Martin also said that I should tell you something about the release plans and open source strategies at DLR. Well, to be sure, there is no open source release strategy at DLR, at least no global one. So if you work at DLR and you think I want to release something, you just go to your superior and ask if you can do it. Then you have to go to whoever is supervising the project and ask if you can do it, and then just put it on GitHub or whatever. Maybe if it's like for the military, you have to ask for export control services. But in principle, it's your own personal choice. So it's still not released. We still have some bureaucratic hurdles inside DLR because we do not have a formal way to do it. It's also still dependent on some project code, and I want to get rid of these dependencies. But I can tell you the license. So we decided it will be LGPL3, and it will be on GitHub, probably in a group KNSAN, which is our department, Communication, Navigation, Satellite Networks. If you want some news on when it's released, probably it's the best to check my GitHub, because I don't think that there will be a German Aerospace Center news about that. So that's it. Thank you for listening to me. Do we have time for questions? Yeah. Yes.
Questions? Repeat the question.
Yes?
The longest fur filter that you can do with this?
The longest fur filter.
Half a second at 100 megahertz?
Sorry, again?
You do like half a second at 100 megahertz?
I'm actually not sure what's the biggest. So the biggest that I tested was roughly 1700 taps, and it ran, I think, 80 mega samples per second. So, yeah.
Maybe another part of the question is there a hardware limitation on the GPU?
Yeah.
To exercise the filters?
That could be so. The limitation, I think, for the filter not, because you go to this local memory where you can store these like constant stuff. So if this memory runs out, then you might be in performance trouble. But I have not come to that point yet. So I think there is plenty of space for even longer filters. Yes, Ben.
So there's obviously been several efforts and examples and implementations of GPU offloading from within GUNI Radio.
Yes.
Which is something that we obviously want to get into the mainline as soon as possible. The major point of concern is always that the GPUs are super high bandwidth, but also high latency to get the data to them.
Yeah.
So based on the work that you've done, what is your opinion of how feasible it would be to basically drop a GPU block in the middle of the radio flow graph, and how would that impact the way your flow graph operates in terms of streaming performance?
Streaming performance. That's a good question. Because there is also another problem with, at least with most of these DSP problems on a GPU, you have to buffer first a buttload of samples to get to this parallelism that you can actually exploit a GPU. So I would guess that the latency from buffering these samples would be higher than the latency from getting them to. Because also this 180 mega samples, okay, it's throughput, it's not latency. It's measured with the data copy from, say, a host to GPU.
Okay.
So.
Sorry, do we have to stop here?
We have to stop?
Yeah.
Okay, then. Sorry, but I'm be hanging around.
I have an announcement. This is the most important thing you're going to hear all day.